So welcome to the first class on probability that I'm offering this semester. So I'd like to begin with some basic concepts in probability. So before I start setting up the structure, let me pose some questions. Okay, the first question you should perhaps deal with in daily life. For example, let me write the question down. So what is the likelihood of rain tomorrow? Or pertinently, you might look at a weather bulletin and it might give you an answer that states that the chance of rain is 10%. The chance of rain tomorrow is 10%. So I'd like to focus on this, on both the question and the answer. One is that in our heads, we sort of have an understanding of what, when we say likelihood or chance, what it actually means to us. Some may use the word probability, some may use likelihood, some may use chance, but we use these words interchangeably. That's one thing that I'd like to sort of focus on in these two sentences. The next thing is the answer, of course. That is, the answer is 10%. So this number means something to all of us. So if you ask somebody in the street, what does this sentence mean? They might give you an answer that differs from what you think the correct answer is. And of course, the other thing I like to focus on is what we have done is the event of interest, right? So the event of interest is the rain tomorrow. So there are three things in the question and answer. One is the likelihood or the chance. One is the event of interest, that is rain tomorrow, and one is the number, that is 10%. So this is a feature of probability and statistics. The feature of probability and statistics. So both these subjects always want to determine how likely that certain things are going to occur. So they always try to determine how likely certain things are going to occur. So one might again determine that this statement is a little too vague, but you should keep it in the context of the question that I stated before. So certain events that you have, and you try to understand how likely they are. So both these subjects deal with differently. We'll try and understand the probability part of it in this course, not the statistics part of it. So for this, to do this, like I said before, I must understand what I mean by likely, what are certain things going to occur. And before I begin the whole structure of understanding these concepts, the first is I like to build a framework for doing the above. And the first question that we like to answer is, what are all the possibilities? Before we determine what's likely and not likely, we need to know what are all the possibilities. Once we know that, then we can set up how likely is that something that we're interested in is going to happen. So that's what I meant by saying in the first question that if you ask somebody on the street that what does it mean to say chance of rain tomorrow is 10%, the person must know what are all the likely possibilities. And then what's the likelihood of the given event of interest. So here's the first definition. So I would call it as definition. Definition 1.1.1. So here I would define it as sample space. So sample space S is just a set. So by definition, it's just a set. A sample space S S is a set. So we'll refer to the elements of S as outcomes. So the elements of S will be called outcomes. So each element in the set is an outcome. And S should be viewed as a listing of all possible outcomes. And S should be viewed as a listing of all possible outcomes. That might happen. So then once you have this, what I will do is I have a listing of all possible outcomes. Then I will call, we will name, how you want to phrase it, we will call the process of actually selecting all these outcomes as an experiment. An experiment. Let me put that in quotes. Put outcomes in quotes. Let me put experiment in quotes. So on my view experiment as conduct experiment and outcome happens, or you can view as the process of actually selecting one outcomes as an experiment. Very good. So that's a sample space. Now let's give a quick example. So let's say I'll take the S as 1, 2, 3, 4, 5, and 6 as my set S as a sample space. Then I would this lists all possible outcomes of a rolling of a die, right? So I would think of my experiment as rolling a die. I'm rolling a die and noting down the outcome on the top. Noting down the number on the top. Noting down the number on the top. So in some sense, S is all possible outcomes that can happen in this experiment. And the experiment is rolling a die and noting down the number on the top. Or you could think of it as S is just, let's say, heads or tails. And you could think of the experiment associated with this as tossing a coin. And noting down the, let's say, the label of the coin. Very good. Now, once we have a list of all possible outcomes, we now should understand what things we're interested in. So that's the next definition I would like to start here. So this is called an event. So definition 1.1.2. It's called an event. And I'll just alert you a little bit. So I will give a temporary definition, not because I don't want to give you the full definition at this point in time. It's just that the precise definition will take some time to develop. So for our purposes now, we will just assume, given a sample space S, an event is any subset E of S. Any subset E of S is an event. So what does this allow us to do? This allows us to talk about how likely is it a possible subset of outcomes can occur. So the definition allows us to talk about how certain events of interest, or a particular range of possible outcomes might happen. Okay, very good. So for example, let's go back to the example that we had before. In this example, we roll a die, S1. So in our example, we count the example. We say example continue. You could say an odd number occurs, right? So you could take the event E as 1, 3, 5 as an odd number occurs. Number occurs when we roll it. That is nice example. So the other remark that I'd like to sort of make before I move on to the next event is that S is also an event. This is the entire sample space in the event. This means that anything can occur. The other thing is that the empty set is also an event. That means nothing occurs. Right? So that's what I mean by all possibilities or no possibilities. That's what the empty set is. Now comes our final tasks. So we've already understood now what all can occur, and we have given a name called an event that will describe how certain things of interest that you want to be defined as. Now our last part in this whole structure is to understand what it means to assign or state how likely something is. Right? So the last part. So what we'll do next is, what we will do is, to each event E subset of S, what we'll do is we want to assign a likelihood, or how likely it is, the chance of rain tomorrow, how likely it is, or what I'll call now as probability. Which will be a number between 0 and 1. So, for example, an experiment was performed, it has a particular event has a certain chance of it. Let's go back to the example again. So what we might say is that, as an example, I might say the following, that I might say this, okay, even though I have not defined it yet, the probability of heads in the toss of a fair coin is half. That means all I've done is that I took the event E to be H, that is heads happens, and I assigned the probability of E to be equal to half. That's what happened. But one has to define this sort of setup. You can't go to every event and every experiment and do it separately. One has to have a formal definition of what we mean by a probability. So these are given by a set of axioms, which I will sort of write down now as the last concluding part of the framework. So let me write the definition. So definition. So these are called the axioms of probability. And even though these were around for quite some time, this formal notation that we're going to use was given by a famous probabilist called Kolmogorov. Which is what we will describe. So now here I will start with two notations that we are already familiar with. Let S be a sample space that we have. It's given to us. And let script F be the collection of all events. So essentially the all subsets of S I will call S. So then I'll define a probability is a function let me keep it up a little bit, is a function P, okay, from this event space 201 such that what outcomes? One is the probability of the whole sample space is 1. That means all possible outcomes are listed in S. That means if you perform an experiment, something in S will occur. And another usual important property is that if I split my sample space into disjoint events, or if I take a disjoint collection of events, it's going to be a countable collection of events. Of disjoint events. So what I mean by disjoint events, I just mean that is EI intersection EJ is empty for I not equal to J. That means there is no intersection between the two of them. Then the probability sums up in the sense that probability of the countable union of the event, that means anything in one of the events can occur. Because they're disjoint, that's the same as the sum from j equal to 1 to infinity, the probability of it. So let me now just quickly describe everything in one summary so that we're all on the same page. Where is my lecture one? Right here. Very good. We go here. Make it a little smaller. We go all the way up. Right. We bring it down. Very smaller. Very nice. Very nice. So here on the left hand side, sorry, it's too big. Very good. On the left hand side, I start off with this idea of what I thought was the key question to understand. So all of us are interested in how likely a certain event is occurring. Then I said, okay, fine. To do that, I need to know first what all can occur. So I defined what's called a sample space. So sample space S, like you noticed here, is just a set of all possible outcomes. So it will be called outcome, and S should be viewed as a listing of all possible outcomes. And you think of an experiment as choosing one outcome in S. Very good. So a quick example that we discussed where one was this example of rolling a die, the other was heads or tails and tossing a coin, and so on. Once we defined sample space, on the right hand side, I began by defining what an event was. So an event, as of now for us, will be any possible subset of the sample space. Okay, so that's an event. It's a temporary definition because event will have to have some structure. We will soon learn later on that we can't assign probabilities to all subsets. We'll learn that later on. But as of now, we'll think of it as any subset. So for example, you could take in the rolling of a die example right here, we could take ES 1, 3, and 5. That is, an odd number will occur. One thing to notice, S is also an event. So is the empty space. Very good. Next, we said we had assigned probabilities to every event. There is a number between 0 and 1. To do this, I gave you an intuitive example. If you toss a fair coin, you expect heads to come half the number of times. So the probability of heads is half. That means probability of E is half, then E is defined as heads. But I don't want to do that. I want to go and do it in a systematic way, in one shot, for all possible cases. So I define S to be a sample space. I take F to be the collection of all events. Then a probability is a function P from F to 0, 1, such that P of S is equal to 1. And it has to have one more axiom, that is, if you have a countable collection of events which are disjoint, then the probability is sum up. That is, the probability of the union is sum of the probabilities. And like I said before, the first axiom is straightforward. It just says that S indeed is a listing of all possible outcomes. That was P of S equal to 1. The second is not as complicated as look. It just says that when you combine disjoint events, the probability sums up. Very good. Let me now go back to my 100% view. So now let me just play a little bit about the two axioms that I said. So two remarks. Axiom 1 indeed says that you think of S as the list of all possible outcomes. And that's all that is saying. If you perform an experiment and S is sample space, then one of the outcomes in S should occur. Axiom 2 is not so complicated. It's not as complicated. It's not that complicated, though it's written in a very complicated way. All it means is that disjoint additivity happens with probability. That all it means is that probabilities of disjoint events, or let's say union of disjoint events, is the sum of all. Very good. Though I must stress that there are several things to stress here. That is when we call this as star. In star, so the several things to stress. One is in star. It's if you know calculus and so are aware of the thing, the series on the right hand side converges. That's what that means. Otherwise, if you don't know calculus that much, just think of it as just adding up countably many probabilities and giving you a finite number. And the countableness is important. The countable additivity is important, which we will stress later on. It's important. It is not enough to assume just finite additivity. But once you have countable additivity, it also implies finite. Right. So such things will not be, this sort of subtleties will come clear as we discuss more and more general probability spaces. This is where we are. So as of now, we have defined a sample space, an event space. So sample space, events, and a probability. And a probability is just a function from the events to 0, 1, such that the probability of S is equal to 1, and if we take countable disjoint events, the probability of countable union is sum of the